When we're multiplying polynomials that are more than just those binomials, we've got to take these one term at a time. So what's going to happen is we're going to take this first term, multiply it to everything in the second set of parentheses. We'll do the same thing with the next term, and then we'll do the same thing with the last term. So basically, every pair ends up getting multiplied together. So let's start with that 4x squared and multiply it to the x squared, the plus 3x, and the plus 4. We'll end up with 4x cubed plus 4x to the fourth plus 12x cubed plus 16x squared. That's just 4x squared times x squared, 4x squared times 3x, and 4x squared times 4. Now we'll do the same thing with that negative x. So we have negative x times x squared gives us negative x cubed. Negative x times 3x gives us negative 3x squared. Then negative x times 4 gives us negative 4x. Finally, let's multiply the 16 to everything. We're looking at 16x squared, 48x, plus 64. So all of those together are the product. So we're going to collect like terms here. We have 4x to the fourth, and a lot of times I'll cross these out as I'm going through. We'll have plus 11x cubed for the 12x cubed minus x cubed. Then we'll end up with 29x squared for the 16x squared minus 3x squared plus 16x squared. Then we'll end up with a positive 44x with a negative 4x and the 48x, and then finally a 64. So you can think of this as extended distribution, where each term just gets multiplied to everything in the second set of parentheses. 5x. I did not mean to go to the next screen. Let me get back. An extension of that extended multiplication would be things like where you had multiple parentheses. So here we have 5x plus 2y to the cube, or to the third power, or cubed, and that just means that we need to have this multiplied out 3 times. I will first multiply the first two together, and then I'll take that result and multiply by the last one. You can only multiply 2 at a time. So if we just multiply these first two together, we'll end up with 25x squared, doing that FOIL, the 5x times the 2y. We'll do the numbers, 5 times 2, and then we have the xy. The 2y and the 5x, that again is going to be 10xy. And then 4y squared for 2y times 2y. We still have that 5x plus 2y. Go ahead and combine any like terms. Sorry, it's 25. So here we do have a 20xy for the 10xy and the 10xy. And now we have a problem similar to the last one, where we're going to take each term of the first parentheses and multiply by the second parentheses. So 25x squared, there we go. Okay, we have 25x squared times 5x is 125x cubed. Then 25x squared times 2y, that is going to be 50x squared y. I usually write my variables in alphabetical order just so that I can recognize later when I have like terms. We'll do the 20xy times 5x, that will be 100x squared y. Then 20xy times 2y will be 40xy squared. Notice here when I have two of the same variable, I end up with a squared term. And then finally, 4y squared times 5x is 20xy squared, and then 4y squared times 2y is an 8y cubed. Let's look for like terms. We have 125x cubed. Then we have 150x squared y. We have 60xy squared, and then 8y cubed, and we're done. We also want to look at problems like this one where we have extra parentheses. What we'll want to do is get rid of those extra parentheses. Here, they don't really do anything other than group that m minus 2. And now we can do our distributing. M times m times negative 2, and m times negative n. Do the same thing on this negative 2. That'll be negative 2 times m, negative 2 times negative 2, and negative 2 times negative n. And then lastly, we'll distribute that n. We get an mn, a minus 2n, and a minus n squared from that multiplication. The last thing we do is look for like terms. I only have the 1m squared, but I have a negative 2m and a negative 2m, so I have a minus 4m. Then I have a negative mn and a positive mn. Those are just going to cancel. We have a 2n and a negative 2n. Those will cancel, leaving us with a minus n squared and a plus 4. And that's it. So these are definitely a little more involved, but we can do our simplifying using that same process over and over again. Now, when we get into some of the factoring techniques, we want to look at first what greatest common factor we might have. It's always the place to start. Since 9 and 27 are both divisible by 9, I'm going to factor out a 9, but they also both have 1 power of x in common, so I'll go ahead and factor out that x as well. What's left here, when I think if I've divided that 9x from the 9x cubed, I'm left with an x squared. And then when I divide the 9x from the negative 27x, I'm left with a minus 3. Now, x squared minus 3 does not factor any further since 3 is not a perfect square. So we're actually finished at this point. So I know 20 was a little misleading because it said factor out the common factor, but it wanted the complete factorization with that common factor factored out. Now, an extension with something like this is where we have, say, 36 minus 16z squared. We can take out a common 4 that leaves us with a 9 minus 4z squared. But unlike the last one, 9 and 4z squared are both perfect squares, which means we can use our perfect square factoring technique. What that says is when you have the difference of two squares, take the square root and add the two roots and subtract the two roots. So in this case, we'll still have the 4, but the square root of 9 is 3. So the 3 will be in the first spot of both of the factors. And the square root of 4z squared is 2z. So I will add 2z and minus 2z. Sometimes the difference of squares are going to look a little strange, and these come up more in calculus than they do in a pre-calculus course, but this is a difference of squares. You'll notice here that we can take the square root of 25, it's just 5, and we can take the square root of z plus 5 squared, it would just be z plus 5. So the square root of 25 is 5, the square root of z plus 5 squared is z plus 5. So when we factor this, we'll do that same difference of squares. We'll have the 5 and the 5. We'll have a plus z plus 5, and we'll have a minus z plus 5. Notice here I did put that z plus 5 in parentheses because I needed to subtract that entire thing. So in this first one, when that's really just 5 plus z plus 5, but the second one is 5 minus z minus 5, paying attention to our distributing. We can simplify this. This is 10 plus z, and this last one is just z, and that's it. You're finished on that one. Another type of factoring is this perfect square trinomial, and it is something that you can memorize, but it's also one that you can just factor when you need to do it. Anytime you have this form where you have something squared and something squared at the end, and in the middle it's 2 times their product, you're always able to shortcut straight to this formula. But of all the formulas, this one is probably the least beneficial to know. The difference of squares and then the cube patterns, those are definitely more important. But here we notice that if our A is X and our B is 2, and I'm getting that from these last terms, taking their square roots, then 2 times AB would be 4X, and this will work. It's actually, it doesn't matter if it's plus or minus, this will both work. And the pattern is that this will become A plus or minus B squared. So in this case, since we have this X squared minus the 2X times 2, and then the 2 squared, this will factor to simply X minus 2, X minus 2. But you don't really have to know this, because you could just factor this one normally. What multiplies to 4 and adds to -4, and you get the answer. So, this special type of factoring, it is always going to be that repeated factor, but it's just not as important to have memorized. It is helpful when you have something that's a little long like this one, noticing that you have the 3y and the 4 when you take the square roots of the end terms, and 2 times 3y times 4 is 24y. So you can go straight to this 3y minus 4 squared using that pattern, but you could do this the long way. You could multiply 9 times 16. You would see that that's 144. So we need to multiply to 144 and add to -24. With a little bit of work, you do figure out that that's -12 and -12. And you can do your factoring normally from there. The last one that I want to do in this video is the sum or difference of cubes. When we have either something cubed plus something cubed, or if we have something cubed minus something cubed, they always follow a very distinct pattern. A squared or A cubed plus B cubed is A plus B. A squared minus AB plus B squared. When you have A cubed minus B cubed, it's A minus B. A squared plus AB plus B squared. And these are just 2 formulas that you remember or have written down to look up later. But it's more about recognizing that that's what's going on. When you see something like x cubed plus 125 and there's no there's no greatest common factor, I start thinking about the cube roots. The cube root of x cubed is x. The cube root of 125 is 5. And you can do that cube root on your calculator, or you can try to think of a number that's cubed will give you 125. So just using that pattern, we have it's x. X here, x plus 5, and then x squared minus 5x plus 25. There I plugged in the x for A, the 5 for B, and you just follow that formula. For 8t cubed minus 1, we'll do the same thing. The cube root of at cubed will be 2t. You do the 8, you do the 2. The cube root of 8 is, do the 8 and the t. The cube root of 8 is 2. The cube root of t cubed is 2t. And then the cube root of 1 is just 1. So you're looking at 2t minus 1 for this formula. And then you have to square that 2t. 2t squared is actually 4t squared. You have to square both the 2 and the t. Then multiply them together, you get 2t. And then 1 squared is just 1. So that's that special factoring with the perfect cubes, whether it's a sum or a difference. The rest of this homework is just looking at trinomials, which is a whole nother type of factoring. So I'm going to do a separate video there since this one was more looking at some of the special cases.